All right. Good afternoon, everyone. If you are tuning in, you may or may not know Michelle already, as she spent some time at Cerner. She is now an engineering manager for cloud control planes at Google. That's in the SRE area, which is why she can give the talk that she is giving for us today. And we're very excited to hear what she has to say.
All right, thank you, Brandy. So I wanted to start this talk by asking a rhetorical question, which is, how do we know if a system is reliable? Typically, this is a backwards-looking question, which means we don't know when we're building the system that it will be reliable. We can follow patterns, we can build architectures that we think will be reliable, but we don't actually know. And so how we answer this question sometimes looks like a scientific experiment, which is we have this hypothesis, we built a reliable system, we create an experiment that we're going to run it in production and give it real traffic from real people and run it on real machines. And then we collect these service level indicators, those measurements around latency and availability and error rates. And we test them against our service level objectives. So we say, okay, this data we've collected, does it meet our expectations? And a lot of times those expectations are represented in the number of nines, right? We want 99.9% or 4 nines or 5 nines. And if it passes, then we say, yay, our hypothesis was correct. However, there's a little bit of a challenge with that type of approach. And it's kind of a challenge with SLOs in general, in that SLOs are very much a craft. Getting them right, it takes a lot of work. And they don't always capture customer pain. And what I mean by that is that you could be perfectly within your SLOs. You could meet all of your nines. You could have only the minutes you were allowed of downtime. And a customer could still be very angry. And the reason they're angry is that they may have experienced a very long outage. And it might be large in terms of blast radius or impact and long in terms of duration. And that experience of like waiting forever for the system to come back up or waiting for the system to behave properly again will be very frustrating for them, even if you were in all of your SLOs. And so on this slide, I have two systems. I have one that had only 5 outages, but 2 of them were huge and impactful. And then I have another system that had a lot more outages, but they were all very contained, either in their duration or their impact. And you have to look at these two pictures and say, if you were a customer and you were being asked to buy a system, or you're wanting to build your software on a system, which one would you prefer? And most people would pick the one that had the smaller but more numerous outages. And just to show you, when I'm saying this, what I mean is these two systems actually have the same number of nines, or they have the same number of outage minutes, or they have the same error rate or failure rate. But how the customer experienced those things is different. And so that experience influences how they think about the product or how they think about the service. And so this speaks to something we've been talking about where I work, which is moving from this idea of reliability to a next level idea, which is dependability. Like, how do we make the system more dependable in addition to being reliable? And so then we have to ask, what is dependability? What does it mean to be a dependable system? And naively, I could say, well, did I break a promise? Did I tell you that I would meet some performance level or I'd meet some expectation and then I didn't meet it? And that sounds great, except that's just SLOs, which we already talked about, which is, we had these service level objectives. If they're codified in contract, then they're the SLAs. But that's exactly what I said doesn't quite work all the way because of customer experience. And so back to this idea of like, we had this hypothesis and we let people use it and we use our SLIs and we use our SLOs and we say, yes, we had a reliable system. The question is, how do we do better? And you could say, well, once you make a contract with a customer and you tell them you're going to meet a certain SLO, that's what they should expect because it's been great. You've communicated to them. It's documented. It's part of the discussion. And then therefore they should expect that and they should plan for it. Maybe they have side processes to deal with the downtime, or maybe if they're building their own software systems, they implement failovers or other mechanisms to deal with your situation or your outage minutes or whatever. And I would love to say that's true. And there are some organizations, there are some engineers and architects that do think deeply about SLOs when they're building their systems and try to manage to them. But I will say most people building software, what they end up doing is they end up designing their systems to Hirams Law. So Hiram is Hiram Wright. He is a software engineer at Google. He's one of the authors of Software Engineering at Google, a book about what it sounds like it'd be about. And he coined this statement that I'm going to show next that I like to call the law of implicit interfaces. But basically, Hiram said, with a sufficient number of users of an API, it does not matter what you promise in the contract. All observable behaviors of your system will be depended on by somebody. And when you think about that, and we think about observable behaviors, it's not just what the software does, it's not just what the code does, it's also the performance characteristics and the reliability of it. And so when I think about this, what I think about is if your customer experiences a long period of great performance from your system, no downtime, no latency regressions, everything's working amazingly, then they're going to expect that is the reality of your system, independent of what was communicated as your SLOs, because the SLO is the contract, but people are going to get used to the behavior. So I like to reword Hirams Law as half the promises people say were never kept, were never actually made. So the thesis of this talk is getting to the point that you can predict and control the scope and duration of your outages so that your customers actually can have this more dependable experience. They won't be surprised by large outages, but they will accept that your system's not perfect, no system is perfect, and they have to adapt to these periodic, small, hopefully, outages and downtimes. So I'm going to change gears for just a second because I want to answer a question that'll help frame this whole discussion a little better, which is I want to talk about operational health. So when I mean operational, I mean like DevOps. But how do we measure the operational health of a system? Now we've moved from reliability to dependability, and now I'm talking about operational health. And there's this organization, DevOps Research and Assessment, DORA, more commonly referred to, that does a lot of research in the space. They basically go out and they survey companies and they ask them about their practices and they ask them about their operational health and how they approach DevOps. And they do a whole bunch of data science to kind of figure out what are the patterns and what leads to success in this space. And they're part of Google Cloud. They're also, if you've read the book Accelerate, this research is what backed that book. And DORA has the 4 measures of health for operational health. And they are deploy frequency, time to repair, change fail rate, and lead time. And I'll go through each of them one by one. So what's deploy frequency? Basically, it's how often can you get code to production, right? Some people are going to measure this in quarters. Some people are going to measure this in months, some weeks, some days, some minutes. But be aware of where you are in that. And then the next measure is when you do push something to production, whether code or config, or any other change, what percentage of them fail? Now, the interesting thing about this measure that I like to highlight is because it's a percentage, not a count, your denominator really matters, right? So the more changes you push to production, the smaller that change fail rate can be because you're not being burdened by like one change making your percentage really bad. And where this comes into play and why I'm bringing this up is if you have large monolithic releases, either because you have monolithic services or because you package a whole bunch of stuff together and you deploy it to the environment all at once, your change fails rate is going to be worse because you only really have a tiny denominator as you're packaging everything together. But if you're working under a more of a closer to continuous delivery model, where each change can be deployed on its own, your denominator is huge. And so if a small number of those changes fail, it's not taking down the whole release or the whole package with it. So the next measure is time to repair. And this is, again, if something goes wrong, how do you get the system back to a better state or back to the original functioning state? And I don't say, how do you fix the issue? Because sometimes repairing the system does not require fixing the issue. And we'll talk about that a little more. But basically, how fast are you at this? So your alarms go off, customer reports an outage, whatever it is. Can you fix it in seconds, minutes, hours, days, maybe weeks? This is a little dependent on time to detection. So if it takes you days or weeks to notice there even is an issue, then you got to add that to the time it took you to fix it as well. But DORA doesn't actually talk about time to detection in their 4 key metrics. And then the last thing is lead time. Now, in the DORA research, lead time is not the traditional Agile definition of lead time. So it's not like we prioritized some work and we started it and how long did it take to get to the customer. It's only the operational piece of that. So the code's written, it's been tested. what is your release qualification and deployment process? And then also as you're deploying, what is your canarying or A/B testing or whatever is your rollout process to get the code into production? So these are the 4 key metrics. Dora has some opinions about where they should be in terms of units and magnitude. But they stress more that the goal is to drive it down. So you assess where you are. If your deploy frequency is monthly, try to get it to every 2 weeks. And if your time to repair is measured in days, try to get it to hours. And then just do that continuous improvement until you get these scores really solid. Now, for the rest of this talk, I'm going to spend a lot of time on time to repair. The reason I'm going to do that is because I'm an SRE, and this is what I spend a lot of my time thinking about, is how do we repair things when they're broken. But there's also this piece that I find really interesting about how all of these metrics are kind of interrelated. And what I mean by that is if you have a really slow deploy frequency, so let's say you only deploy once a month, and something breaks in production, and the way you want to fix it is you want to actually patch the code. You want to fix the code and roll it out. You're going to you have 2 choices. You have to wait to catch the next deployment, or you have to go around and circumvent your own deployment process to get it out fast. And both of those things are time consuming. They take time, and that impacts your time to repair. The other thing is that if you have a high change fail rate, let's say because you're packaging a lot of things together to push to production, when you push that fix to production, any other change in that package could cause an error, and that would make you have to roll back the whole thing and go back to a previous good state. And then also lead time. Obviously, if you're fixing something in production, you want to do your QA process. You want to make sure that the code is solid and it's been tested and it's been reviewed. And so the longer that is, the longer it takes you to get that fix in production. Now, this leads to kind of a chicken and egg problem that I've seen in a lot of organizations. And it goes something like this. You have a somewhat slow release pipeline for whatever reason, or deployment process. Maybe you do once a week, maybe you do once every 2 weeks, but for some reason it's kind of slow. And you roll something out to production and it breaks. And so then people come back and say, okay, well, how could we have stopped this from happening? How can we have prevented this issue from even hitting production? And so you add more QA through tests, maybe through human review, maybe through like manual testing. Maybe you add gatekeeping. So you add like some sort of gateway, a quality gateway. Maybe you add a change control board. Maybe you go ahead and say, oh, deploying into production has to have VP review or something crazy like that. And so you slow down your release process more as a reaction to the fact that you've experienced this breakage. And then what happens? Well, when you finally do release, you're pushing more changes because you've accumulated more as part of the slower release process. And then you're more likely that something breaks. And so then you come back and you slow down your release process and you add more QA and you add more testing. And you get in this terrible feedback loop that suddenly you're moving very slowly and you can't understand why anymore. And you don't seem to be stopping things from failing in production. And so my solution to breaking out of this cycle is to figure out how you can have a fast repair time without relying on code changes getting to production. This is something that we're trained very well at in SRE, is to figure out what can we do to fix the system that doesn't require us understanding what actually broke it. Now, for some people, that might sound really weird. Like, how on earth can you fix the system if you don't know what broke it? And the answer is we take time to build what we call generic mitigations. So we figure out what are the things that you can do to the system that, independent of what caused the error, will move the system to a better state. Now, it's not a guarantee, obviously. It's more we'll try things and see what works. But this is what we do in order to get out of that feedback cycle of not being able to repair the system because releases take too long. And a good example of a generic mitigation that a lot of people already do is push button rollbacks, right? Most likely something changed. That's what caused your outage. So the ability to go back to the previous version of the system before that change is probably the fastest thing I would call generic mitigation, because you don't actually have to know which line of code broke the system. You're just going to roll it all back. But we'll talk about some other ones, more interesting ones, as we go along. Now, these generic mitigations are going to be useless to you unless you practice them. And this is part of my general philosophy that I believe about a lot of things in software development. If something is more painful, you should do it more often. The analogy I have is that if you clean your house once a week instead of once a month, there's a lot less to clean overall. I think this applies to a lot of software development things we do, like testing. Testing more frequently is less painful than testing infrequently. Integration, we want to integrate early and often. And I also say the same thing about planning. A lot of times when planning is painful, people want to take a step back and slow down the planning process and do it less frequently. But you actually get better at planning by doing it more frequently, which I think is part of what Agile is trying to advocate for. So we want you to build these generic mitigations, and we want you to practice them and use them. But let's start with how you build them. So I'm going to talk a little bit about control theory to kind of address this question. And control theory got really popular recently because of observability. And observability is one half of control theory. And it basically says, can I infer the system state from visible outputs? That's the textbook definition. Controllability is the other side, which is, can I manipulate the system to the state I want? So basically entirely through inputs, can I get the system to where I want it? One way I like to think about this is observability helps your time to detection, and controllability helps your time to recovery or time to repair. And then another way to look at it is observability is like, how good are your logs? And what do you build on top of those logs? And controllability is how good are your mitigations? And we want these things to be good. We want them to be things we can actually rely on and use. And if we have really good observability and good mitigations, we can combine the two to create some automation in our system. So we can have an alert that detects something and automatically applies a mitigation. And if you have that just running, suddenly you have a self-healing system. So I'm going to spend a little bit of time on observability, but not a lot, because I'm sure there's tons of better talks and tons of better information out there, because this has been a very popular topic and there's people who specialize in this. But I feel I need to cover it. So typically when we talk about good observability, we really mean structured logs and metrics. So we want the logs to not just be a dump of information, but actually have fields in it that can be sliced and diced and queried and used to actually like filter for graphs and things. And you also want metrics. You also want numbers. You want to know things, not just what happened in the code, but like, information about performance or other pieces of information. And when you have all this structured data, then you're really looking for your tools to give you that ability to handle how much data it is by allowing you to, handle all the possible values and handle all the possible fields that are in the structured data. And so that's generally what you want in observability. The reason why this became important is because as we've moved as an industry to more and more services communicating over, unreliable networks, we run into this problem where when something breaks in our system and the whole system seems to be failing, it's really hard to figure out where to pay attention, like where's the problem probably coming from. And so this is the Holiday lights problem of microservices, in that you have a strand of lights, one bulb goes out, but it breaks the circuit and the whole thing goes out. And then you have to figure out which bulb it is. And if that's a system, like a set of microservices interacting, you don't want to have to do the binary search approach of figuring out which one is at fault. And so you want observability to answer the question for you. Now, I do think as an industry, we've gotten really good about doing this in terms of errors. So when one system starts returning 500s or starts failing in some other way, we can usually in the structured log find the errors and figure it out. Where I've seen struggles lately is it comes to latency. So, and I'll talk about this a lot more, but basically you have one component in this big distributed system that is slowly getting slower and slower and slower over time. And then suddenly we cross this threshold where its slowness has this cascading effect to bring down the whole system. And then it's not terribly observable, that creeping up of delay in this tightly woven architecture. So that's my quick little talk on observability for this. I'm going to move to controllability now, because that's what's really interesting to me as part of this conversation. So to me, controllability means having good mitigations. And the characteristic of a good mitigation is it's safe, it's generic, it's usable, tested, and reversible. To kind of put this all together, basically, I want to be able to run the mitigation without being afraid it's going to make the problem worse. So I have an outage. I want to be able to say, yes, I can run this command, and it may not get me out of the outage, but it won't make it worse. I want it to be generic, and that means I don't want to have intimate knowledge of the component that's broken or intimate knowledge of the code to be able to run it. I want to be able to say, I can run this even though I didn't write the code. I want it to be usable, meaning that in the heat of the moment when I'm dealing with this outage, I want to be able to not have to go flip through manuals and try to figure out some cryptic commands. I just want to be able to it to be obvious and I can use it. And then it's code. So I actually want it to be regularly tested, just like code. And I want to have confidence that it still works even as the system evolves. And lastly, I want to be able to undo it if it didn't help, so I can remove that variable from the system. But above all, it needs to be safe. That characteristic that you can feel confident that you're not going to break the system more by executing this mitigation is really important. Now, the bad news I have is that I do believe systems need to be designed to support good generic mitigations. I think it's really hard to go tape these on or attach these on at the end when you've missed some essential characteristics of a well-designed system. That isn't to say that if you're working on what you would call a legacy system that you're completely lost, like you can't do anything. What I would say is that basically try to find pieces of that system that you can manipulate and then refactor and evolve over time to build more and more of these. And so what do you need in a system in order to build a good generic mitigation? Well, one of the most important things to me is item potency. So basically, you're going to want to be able to perform operations over and over again and not have them have these weird, nasty side effects. That's part of that safety piece of it. You're going to want loose coupling. Again, loose coupling allows you to kind of reason about what is the blast radius of modifying a piece of data or modifying or invoking some command on some component. And then, of course, high cohesion always goes hand in hand with loose coupling. And then encapsulation helps because a lot of times when we're trying to do these generic mitigations, they'll be very much about the data. So for example, let's say you deploy a change to production that now whenever you go and write some data that's very important to your product, it corrupts it just a little bit. And you've detected this and you want to fix it. And you could, wait for the code fix to come in, and you could then try to figure out, like, how am I going to clean up the data? Or you could have some sort of generic mitigation that reconciles data. And when you have that, you want that to work because that'll work better, let me say, if you don't have everything trying to read all the data all the time. Like you have a better chance of accomplishing that if you've isolated or encapsulated your data. And then related to that, systems should have some tolerance for eventual consistency. I've worded this as inconsistency tolerance. And they should be robust, meaning they should be able to handle errors and other issues with some gracefulness, sometimes gracefully degrading. And then another thing that's interesting to me is the Cerner concept of passivity. Passivity was coined by David Edwards. And to me, it's really interesting because I do think passivity gives you some tools for generic mitigations. And it wasn't intended for this. I think intended it was meant to be more of a cultural thing of like, hey, if you break something, you should probably fix it. But I like it because it constrains the way you change the system in a way that allows you to then, if that change breaks something, still have the rest of the system still behave normally. I think passivity is very closely related to Hirams Law in that it is a little bit about what promises do you make to your users or your customers, and then how good are you continuing to honor those promises. And it definitely carries that idea of in passivity, everything's a promise. So I like that a lot. And also, like I said, that cultural ownership thing of, well, if you break it, you own them breaking it. So let's say you found a piece of your system that you're like, yes, we do actually do idempotent writes, or we do actually have this really great encapsulation piece, or this thing is really loosely coupled. And so then you think about, okay, in case of an outage, what would I do to fix this? So if it's a stateless system, like the most obvious thing you might do if the system's malfunctioning beyond rolling back might be to restart the thing. Because what might happen is it might be a problem with, garbage collection. It might be a problem with, deadlock. It might be a problem with, memory. And so like your generic mitigation could be, I'm just gonna restart this thing. And you could have this be like a playbook somewhere with all the places you have to SSH and all the places that you have to log in and what commands you have to enter. Or you can make it an API, and then you could build tooling on top of it instead of just having a shell script somewhere or a playbook somewhere that you could execute. Another generic mitigation you might do is you might have a intent-based set of logs. So basically what I mean by that is that you somewhere, when a customer's asked for something or a user's asked for something, you've logged what they wanted. And that looks different, of course, than what happened in the system because you applied all your business logic and you've transformed and converted things. And you have the ability to take that log of what the customer wanted, and you have the ability to say, okay, play this forward in the system back to the state that it was. And that requires that idempotency again, because you're basically replaying an operation that already happened on the system, but you are able to do it in a way that you can maybe inject new behavior, or you can tweak something to make it work better. And so again, that should be an API. Like I can restore to a previous state of an object or a set of objects. And basically, you start thinking about, can I quickly recover to a good state? And if I can't, what would be the tools in my toolbox that I would want to have to allow me to do this? And since these tools are going to be very powerful when you build them, like for example, one tool you could have is the ability to go to an entire backup of your database and then restore it. That tool is very heavy and has a huge blast radius if you do it wrong. And so you might want, as you're designing these tools, think about, well, how would I safely limit the blast radius of the fix to only things I cared about? Or how would I safely limit it so that when I want to try it out on a small subset of the data first? And you might say something like, well, maybe I just want to do, in your case, one patient at a time. So let's say we want to restore a previous version of a single patient, because, and then we can verify that what we wanted actually would be fixed, that the error that we've encountered would be fixed. And then we could build this bigger automation that would say, okay, now we have this other automation that can do it, on multiple patients and sets of patients. Well, if you build something like that, you actually get to a state where you're actually starting to build some mechanisms for your customer to use. So, you might be able to allow your customer to restore to a previous version of a patient if they'd accidentally done something wrong with the patient, not just we had a bug fix. And so the reason I'm talking about this is I do think that observability and controllability are requirements of your system that you have to kind of think about as you're designing features, as you're building features, or even treat as like first-class projects. I think whenever you try to solve these problems by just adding something after the fact and treating it, like it's not real software, either through scripting or, somebody just has something on their local drive that's not even checked into source code management, then we don't get the full power that these things can offer us if we actually treated them as first-class APIs or first-class software development problems. And since they're requirements of the system, then we need to continuously test them. We need to do regression testing on them. And that's because as we change the system, as we make small changes, add new features, fix bugs, there's always this chance that you will introduce a change that breaks your ability to do the generic mitigation. And we don't always notice that this happens until something really bad happens. So like if you broke your generic mitigation through some software change 3 months ago, you might not realize it, and then until you're trying to do something in prod to fix an outage, and lo and behold, and you're finding out at that moment that it's broken. So continuously testing this as part of like a regression testing suite is important. And the reason to do that is to get out of this pattern of not seeing that problems are happening until it's way late in the game on fixing them. The longer that you get away from a change happening and understanding that it broke something, the harder it is to fix. One reason is because the person that wrote the original code has moved on to a new project, and now you're asking them to context switch back. Or if they can't even help because the other project's a higher priority, they may have to delegate that task to someone who is inexperienced with the code, doesn't really understand it, and it'll take longer. You also end up in this weird problem of like changes can be built on top of other changes, and it's hard to kind of propagate the fix forward in the system if there's too much interdependency. And this again speaks to good design practices. This is not as bad if you have loose coupling, high cohesion, encapsulation, and these things. So, okay, so how do we find that we broke something, our ability to fix production through generic mitigations? How do we find that we've done this fast? One thing gaining popularity in the industry is this idea of an architectural fitness function. So basically, it's an idea that you should have tests even for architectural constraints or architectural desires in your system. And I think this fits in that category. The perfect example of this is that a lot of people, when they're doing their disaster recovery planning, will say, okay, we're going to have backups and we're going to be able to restore from backup. But they never continuously test restore. Like they have alerting to know that the backup failed, and they have tests to make sure the backup happened, but then they don't just continuously run the recovery over and over again and make sure they can actually restore. And a backup is worthless if you can't restore it. And then that speaks to that theme I said, which is something is painful, do it more often. So something like your disaster recovery strategy, if it's painful to do it, you should do it more often because you'll get better at it. And maybe you'll automate away some things that are painful. So I'm going to come back and I'm going to talk a little bit about how we test systems in a way that allows us confidence that in an outage, we will know what to do, that we'll have the observability we need, and that we'll have the controllability that we need in order to detect the issue and repair it. And so I had this mental model of big distributed service systems where I think of them like a directed graph. And each circle in this graph is a component or a service. And each arrow is an invocation or a call of another component or service. So it might be, a call to a RESTful API. It might be an RPC. It might just be a function call, like just calling another function. And in an ideal world, these systems are designed in a way that they are aware of the actual performance of the component they're calling over a long duration, over a long enough sample period. But usually that's not the case. And so I'm going to say each component in this distributed system has these classes of performance that it's going to have. And for performance here, I don't just mean speed, like, how fast can you execute something? I mean, like, just generally, how is the customer experiencing the behavior of that component? Back to the whole Hirams Law idea. And so every component in a big system is going to have that green behavior. And the green behavior is the system is working under ideal circumstances. So this is, garbage collection isn't running, the network is reliable, the clocks are all synchronized, the machines are not having any kind of, contamination or failures or anything else like that, and just everything's running beautifully. Then the yellow is, because we're good engineers, we've designed the system to accept that sometimes there'll be packet loss, and sometimes bits will be flipped, and sometimes a machine will fail, and sometimes we will have garbage collection running while we're trying to do something else. And so we designed the system such that, hey, under this scenario, we think the system can still perform. It's not ideal, but it can still perform. And then we have the orange, and this is when the behavior of the system starts slipping out of that, yes, we've planned for this performance. So this might be, you have some contention in the system that you didn't expect. This might be you're being called at a load you didn't expect, so you're not scaling. This might be more machines failed than you really realized or planned that would fail. And so at this point, this orange circle is the behavior at which you want to be alerting. So you want to be alarming on this point, because then you're finding the problem before it's actually an outage. And this alerting on orange really is dependent on that structured logs and that good observability and those metrics that you need, because otherwise you're going to be stuck waiting till red. And red is the system fails here. And I think you have to test to understand these limits. Like, you have to play with the system a lot and to understand these limits. You can't just kind of cross your fingers that you know what yellow is or you know what green is. So I have this theory about outages. My theory about outages is that there are three things that tend to lead to an outage, besides changes. Obviously, changing software leads to outages, but we have to change software. The three things that lead to an outage is one of your users of your system, whether through automation, a service, like if you have a service calling another service or whatever, someone in your system using your system decides to start depending on your green. So they depend on your idealized perfect performance. And the reason that happens is Hirams Law, which is that if they have this long period as they're designing their software, that they're only experiencing your best behavior, then that becomes their new expectation. That becomes the contract. So the one way to think about this is that if, under idealized circumstances, your service returns in 10 milliseconds, but you're really planning that, like, oh, my SLO is like 100 milliseconds. If a customer experiences 10 milliseconds while they're building automation on top of your software, then what they're going to do is they're going to say, oh, for my retry logic, maybe if I just did 5 times the 10 milliseconds, I'll be good. And so then that's where they get that dependency on your idealized behavior that you didn't understand. And so the outage occurs because your software goes back to yellow or it goes to orange, and then their system breaks. And again, this is Hirams Law. It's just going to happen because people are going to expect what they've perceived to have been happening. And then what you're going to have is you're going to have this rough socio-technical problem or an organizational problem, where what's going to happen is the people that wrote the code that depended on your idealized performance are going to go to you and say, what gives? You just got 5 times worse than you were before. And you're going to respond, but I was an SLO. And nobody wins in that conversation. Like, nobody wins in that conversation because it just doesn't go well. You would like to believe that the SLO people would win, but they don't. And so how do you prevent this from happening? Like, how do you prevent customers from coming to rely on perfect performance? And what it is that you have to occasionally, through continuous testing, either they or you have to find a way to practice regularly what would happen if performance slowed a little bit. So latency injection, you can have this mock implementation that you schedule and plan for some testing with, where you intentionally let things slow down a little bit and see what breaks in the system. And you could do fault injection, where you could suddenly ramp up the rate of 500s return from your service and see what happens. You can also do, the tons of things covered by Casey Rosenthal and all those folks in chaos testing, where it's like, okay, well, what can we do to bring down parts of the system and see what happens? And as I mentioned before, also this idea of like regularly doing your restore testing, because you do want to understand what happens in your system when you have to take it back in time a little bit through that backup and restore process. And you may be asking, like, great, this sounds scary. And I'm not saying do this in production. I will say it would be great if eventually you get to the point you're doing in production, that you trust everything going on your system so much that you can do this. But first, just start where you can. Latency injection and fault injection can actually start in unit testing. If you're doing a good job of mocking out your errors and exercising your timeout behavior, you can catch a lot of issues in unit testing, especially if you have like bad behavior that leads to an infinite retry. You can definitely catch that in unit testing. And then once you get good at that, then you can move on to doing it in maybe your staging or similar environments that you might have. And then if you get really good, then maybe you consider production. And then again, this is back to the part of something's painful, do it more often. This testing should occur frequently. It shouldn't be like just something you do once a year. So that was the first reason outages happen. The second reason outages happen is in this deep chain of nested service dependencies. A service slips to red. It's going to happen eventually. It does happen. And then that one service slipping to red has a cascading failure in the system. And you have to kind of figure out what went wrong, and you have to figure out how to fix it. Now, I've seen in outages where people have had this experience of, well, crap, this dependency I had was essential to me, and it went down, and there was nothing I can do. And that's an opportunity to ask yourself, well, was there a generic mitigation? Could you have failed over to another system? Could you have done a graceful degradation where you're using, stale data, but it's still okay? And start asking yourself, okay, if I want to be able to do these things, how would I design the system to be able to do it? And then what operational APIs or mitigation APIs would I want to have in order to make sure that I'm able to do this with good tooling as fast as I possibly can and feel safe about it? So again, it's back to like, how do we get the state where we're like treating this as part of the design of our system, the ability to get it to a better state. And then the third reason I see outages happening is you have what I call a pathological customer. This doesn't mean they're a bad customer. They may be well-intentioned, well-meaning. They probably have no idea what they're doing is wrong, but they do something to your system that your system wasn't designed to handle. It may be they have an infinite retry loop and they accidentally do a denial of service attack on you. It may be that they send you data and that exercises a path through the code that you never had planned, and then suddenly your service starts returning 500s on everything. Whatever happens, you're going to have these situations where a customer is the trigger that caused your system to fail. And it's one of the most common cases when your failure is not related to a change. And to help with this, the thing I actually pitch and propose is to use what I call our pathological probers. So a prober is a piece of code whose job it is to regularly call into your service or into your component, or maybe it is something that exercises your UI over and over again. And when we tend to write these systems that do this, these jobs or these tools, or as like we said, I call them probers, we tend to focus on, again, the idealized behavior of customers. We focus on, what would they do if they did exactly what we expected them to do. And part of that is because, we want to make sure we're testing the happy path of our code. But I think also part of it is almost this lack of imagination on all the weird things that customers could do. And so one of the things I suggest doing is actually having that brainstorm session of what are the weird things a customer might do to us? And why don't we create some code that tries those things? And then we run those things and see how the system responds. And then you can have mitigations like the ability to load shed a particular customer who is calling you too much in order to let the rest of the customers actually have the functionality they want, but you go contact this customer and talk to them about what's happening. And so then that's another good case of a mitigation API you might want. So the idea of this whole discussion, and I know there was a lot of path to get here, but the idea is, we started with this idea that, reliability is a scientific experiment. You build a reliable system as your hypothesis. And before I was saying you run it in production on representative machines with representative traffic, and then you see what happens and you measure it and you see if your hypothesis is right. And the ideas here that I presented are basically the thought that if you get really good at fixing outages fast, like when something happens, you are really good at making sure the customers don't feel it. Then you can get to this point where you can actually start testing your assumptions about whether the system is reliable or not through fault injection, through these pathological probers, through chaos testing. And it's not scary because you can fix it fast. You have tools to fix it fast. And then as you're exercising those different problems that you're going to experience that lead to outages, you can fix them. And then you get to this point where you're really confident when you're running in production that you're actually going to meet your SLOs and your SLIs, because you've narrowed the blast radius and the size of the outages that you're going to experience. When I first put this talk together, I was thinking about calling it If a Tree Falls in Production, because it was kind of my funny way of thinking, if you have outages, but no one ever notices, then they're not really outages. I mean, you still have alarms and you still have these mitigations you apply, but from a customer perspective, it's not really an outage if you get the time to detection and the time to repair down really small. And then that allows you to predict and control the scope and duration of your outages, which is what customers want to experience. They want to experience this predictability. And as part of that, we've been able to shift the conversation of how do I know if a system is reliable from a backwards-looking one into a much more forwards-looking one, which is where we want to be. And then the end goal is we'll be driving to better operational health by pushing all these things down, because if we have time, we have a really great time to repair and time to detection. If we can trust those things, then we can actually do things like deploy more frequently and trust that we'll be able to fix things if they break. And then that frequent deployment makes it less likely that the set of changes we're deploying are going to fail. And then this all together makes us have better lead time, which of course allows us to get good features in our customers' hands faster. So I pulled this content from a lot of different resources. I wanted to point out a little bit of a few of them if anybody's interested. I will say that this talk is built on top of Dave Renson's Less Risk Through Greater Humanity talk, because I did assume that everyone listening understood that systems will fail, that you can't be perfect. If you have not watched that, please do. It's a great talk. It's in your own CernerEng YouTube channel. The other thing I looked at was Sidney Decker's paper, Drifting into Failure. It was a great paper. And then, of course, the Dora research is always great. And then, as I mentioned, Hiram writes Hirams Law. And so with that, thank you very much. And I believe that Brandy will be switching to Q&A.
I am switching to Q&A. So the first question is around MTTR and MTTD. What do you learn from those metrics? So what kind of decisions, how are your decisions focused? How does your attention flow? How do you coordinate work, et cetera, with that data?
Okay. So typically what we have done is we look at this data as some sort of operational review periodically. And we look at not just how is this number bad, but why is it bad, of course. And then we look for categories of problems around what made it bad. So for example, if you have stateful services, your long MTTR is probably going to be data cleanup. And data cleanup usually takes a while because a lot of times you're trying to surgically craft updates, inserts, deletes, whatever, to make sure that you fix only the things that you really wanted to fix and you don't break anything else. Or I know if you're in a big data MapReduce world, maybe you rebuild the world every time because that's the safest thing, and that takes some time too. And so, for example, if you see that that's the pattern, then that's the project you go prioritize. You say, okay, we're gonna go build around how do we more quickly clean up our data in an outage, and then try to craft it as a generic problem instead of these surgical problems of, okay, I want to be able to update just this one field under these strange conditions. And then maybe you're more stateless and that's not actually what your problem is. And so then maybe you look at it and say, okay, well, we tend to have more outages due to deadlocks. And so then what we want to prioritize is, okay, well, how do I get myself out of that? Do I just want to restart the system? What do I want to do here? So I hope that helps.
Yeah, I think so. And then, so the next one is, if people are relying on an idealized version of your system and making bad assumptions, and you're attempting to keep your system near its idealized state, do you reach a point where you just have to say no to your customer? Like, is there a point of diminishing returns? And if so, how do you know when that is?
Yeah, so that's very good. So I will say if the customer expectations are becoming unreasonable, meaning that they can't tolerate any network connectivity issues, we know that is an unreasonable request. And so that's definitely an immediate breaking point of where you have to say, okay, I'm not going to give you what you're asking for. What I think so, and that's an unreasonable customer, and it's very easy. Immediately, you just kind of go sit down, you have the conversation, and you explain like I can't deliver on this. I think the harder problem is when what they're asking for sounds reasonable, but then is really expensive to go deliver, and you know the customer's not willing to pay for what it would cost to deliver it. In those conversations, I feel like exposing that cost and describing what it would take, and like having like a menu of options tends to work well, especially if we're talking internal customers. That really works well. That kind of like just making it a business decision. So sure, we can give you the 5 nines you're asking for, but you need to fund a team of this size for this many years and give me this much hardware. And that works really well. If it's external customers, I mean, you get sales and product and everyone involved and try to figure out how to politely have that conversation. And then what usually happens, though, is you've decided an SLO that was really loose because you were worried about the worst case behavior. And your consumer is experiencing your idealized behavior. And the right answer is somewhere in between, where you need to realize that you can't have just SLO'd for the worst possible case, but you also can't meet their expectations, and so you kind of meet somewhere in the middle as a compromise.
Okay, so the next one, to the person who asked it, I'm going to reframe it just a little bit because I want to make sure that we actually get a good nugget out of this one. So, how can we remain generous with our customers when they are making unreasonable demands? Like, what's the thought process and what's the culture you have to cultivate so that you're being mindful of your customer needs and not reaching a point where you're resenting them, for example?
Yeah. There's a great talk by an SRE named Cindy that I'll get this to Brandy and she can share it somewhere, about the path to customer-centric SLOs. And so it's the idea that part of crafting your reasonable expectations of the system, what you decide are reasonable expectation of your systems, is listening to your customers, really building empathy for what they're going through and what they're trying to do. This does not mean asking your customers. I will say a number of times in my career, I have foolishly thought, I'm going to ask the customer, or I'm going to ask product, or I'm going to ask strategy how they expect us to perform. And of course, the answer I get is perfect. They want real time, streaming, and they want, no failures, and they can't tolerate eventual consistency. And that's why you don't ask that question that way anymore. Instead, you go listen and find out what their problems are and what they're trying to do and the workflows they're trying to accomplish. And then it's our job is fun because we're problem solvers and we're creative problem solvers, and we go figure out, okay, what can we build that actually helps them? A great example of this is I will actually pull from my Cerner time. I remember one time having this conversation about latency expectations, and everyone kept saying real time or near real time. And then when we actually asked some folks about what was the clinician's workflow, we realized that they only checked the computer every so often. Like they would look in the morning and they'd go about their work, and then they'd come back to their computer, and then they would go out and do some work, and they'd come back to the computer. And if the user is only checking, once every 15 minutes or once every hour, then the definition of real time is not sub-second, right? It's something else. And so that gave us the wiggle room to be able to say, okay, we were projecting unreasonable expectations just because the terminology wasn't consistent.
All right. Here's another one. Where have you seen effective motivations or influences with teams to get good mitigations into more automated, defined parts of the system, as opposed to living with manual interactions? So where human operators are basically still tolerating with manual tasks. So how do you motivate people to do better?
I have always found that when folks move into what we call a scarcity mindset, which basically is when you feel something is really precious and in limited quantity, that you start making suboptimal decisions about that resource, and your time can be one of those resources. So your own mental capacity and time can definitely turn into something that you feel is very scarce. And it is really hard for a team that is drowning in operational load, manual operational load, to free themselves from this short-term tactical response mode into that creative strategic mode. And so that's where you really need managers and your leaders to go fight for the space, uh, either through additional staffing and saying, okay, we know it's going to take us a while to hire these people. We know it's going to take a while to ramp them up. This is not an immediate solution, but we do want to get out of this space eventually. So we're gonna staff teams that are going to be, their job is to not take on more operational load. They're going to handle this. The other way to do it is to, refuse some operational load, distribute it differently, find, someone else in the organization that can take that work on. That's a big part of SRE principles you'll see sometimes is like handing back work to the devs. You may not have that option, but that's one tool that you can use. And I genuinely believe, and there's other options too around like how do you get the people that you depend on to then prioritize this work, and you go work through leadership and you do math and you show how much time your team's spending on these manual interventions and how much it's costing and the time to repair, and you present like a report and get it prioritized. But I do think generally when people ask me like, why isn't the team motivated to do this work on their own, or how do we get the team motivated, I think sometimes we're missing the bigger picture of like, have we created the space for this creative thinking?
Yeah, that makes sense. Okay, I think we've got time for one more because we have 3 minutes left. So how do you balance striving for more functionality versus the desire to have a stable and easy to work with foundation?
So the answer from my current employer would of course be error budgets. And so basically we would look for, something being out of SLO, or more recently, because of this dependability concept that I've been talking about, sufficient pain that may have been felt by the customers despite not being measured in our SLO. And we basically invoke the error budget. This doesn't always mean freezing. I think a lot of the content out in the world about error budgets means that, oh, you freeze. Sometimes it does mean freezing, but sometimes it actually means basically the reliability folks get to steal the roadmap, and they get to reswizzle priorities, and they get to restructure investments so that a greater percentage of engineering time is spent on reliability and the system, as opposed to cranking out new features. That's still very backwards looking, and I don't know if this question was meant to look for something more proactive. My proactive answer is when you're giving estimates, never cut out reliability work, just bake it in. Don't treat it as a separate line item. Don't give anyone the opportunity to take a red pen and cut it off. Always vertically scope your work so that if there's someone's going to take a red pen and cut something out, it's going to be another feature.
Okay, I lied. For old time's sake. Yeah, but we work in healthcare, Michelle. How do we put our systems at risk since we work in healthcare?
Yeah, this question's always amusing to me, and I've heard it a lot, both when I was at Cerner and when I was not. And I'm always surprised by the question, because inherent in it is there's this assumption that if you work in a different business, you are a little more complacent about quality or performance or any of these other factors that make software great. And having worked for a few other companies, I don't see that. Like, I don't see that the industry changes the way people approach quality and the way they care about their users and how they want to protect them from pain. Now, I know you can say, well, the consequences in our healthcare are worse, and that's typically what people say, as opposed to if you're writing a streaming platform or whatever. However, I work on infrastructure, so the control planes that we run on, that we support, basically support a lot of GCP products, but most notably GCE, the compute engine, and banking companies and healthcare companies and all sorts of very critical infrastructure companies build on our products. And so we do these things, we do these practices, and so do other companies, with that in mind, that we actually believe this is how you get more reliable and more dependable software, and that's why we're doing it. It's not because we don't think there's consequences to our work.
Excellent. We are out of time, so I think that is all. But thank you for your time, Michelle. And we will have this video posted out for anyone who wants to watch it or share it. And we can also reference back to some of the resources and other talks that Michelle referenced in the middle of this one. So thanks.